Properties of logarithms extend the properties of exponents because logarithms are the inverse of exponents. So it helps to take a look at the properties of exponents first. Here we realize if we are multiplying like bases, then we add the exponents. But remember, logarithms are exponents, so when we add logarithms, we're going to multiply their inputs. Another important thing to point out is notice here when we're multiplying like bases, we have two of them. And then after using the exponent property of multiplying like bases add exponents, we now condense to a single base. With logarithms, it's the same thing. For the product property of logarithms, when you are adding two logs with the same base, then you condense that log to that base and then multiply the original inputs of those logarithms. So to stress that one more time, logarithms need like bases to simplify. And a common misconception with the product property of logarithms is to think that if you have in this case, the common logarithm of the product of two terms, that you could then take that and rewrite it as the product of two logs with that base. That is not the case. Remember, you have to switch operations. So multiplication is shortcut for repeated addition. And then here, since we're multiplying, that means we need to introduce addition. You must always change your operation. So this would properly be the following: the common log of A plus the common log of B. Sometimes you'll want to expand the logarithm like we are doing here. Sometimes you'll want to condense the logarithm like here. So here we want to express it as a single logarithm, simplifying if possible. So we have logs with like bases, so then we can add them together by switching from addition to multiplication in the following fashion. So we condense the log base 6 to a single copy and then multiply their inputs. And 4 and 9 make a product of 36. And remember, the logarithm represents the exponent that takes you from the base subscript to the input of the logarithm. So what do I raise 6 by to get 36? And the answer is 2. To use algebra to show you how I got the log base 6 of 36 to equal 2, I have over here showing that I set it equal to x. Using algebra means to use variables. And then rewriting from logarithmic to exponential form. Keep that in mind whenever you are in a form, exponential or logarithmic. If you can't figure it out, given the form, switch it. So here I go from logarithmic to exponential using the definition of logarithm. The base gets its exponent, and then it's set equal to the result, which was the original input of the logarithm. So then 6 to the power of x is equal to 36. So you could either just eyeball and see that you could square 6 to get 36, or you could use a property of equality that says that if you have like bases, then you must also have equal exponents. And so then the answer is 2. Noting that there's no x in the original problem, I was just temporarily using the benefit of algebra to come up with how this logarithm simplified to the number of 2. The quotient property of logarithms associates subtraction with division. So now, if I have dividing like bases, then I subtract exponents. Well, logarithms are exponents, so if I subtract logarithms with like bases, then I condense that logarithm into one with that base, and then divide their original inputs. And it's always left to right. So this one goes in the numerator, and this one goes in the denominator. A common misconception is to take the log of a ratio, in this case a on b, and set that equal to the ratio of the log of the numerator of that ratio with the log of the denominator in that ratio. That's not correct because we're going from division to division. There must always be a change in operation, so it needs to go from subtraction to division or vice versa, giving the following. The log of A on B expands as the common log of A minus the common log of B, remembering that the common log is implied to have base 10. To express as a single logarithm and then simplify when we have the subtraction of two logs with like bases, I then condense to one log with that base of 3 and then do the quotient of 54 on 2. I simplify, giving the common log base 3 of 27. And I ask myself the question, what do I raise the subscripted base of 3 by to get 27? Because the logarithm is equal the exponent in that trio. And that's why the answer is 3. To look at it another way, we have log base 3, and then 27 is 3 cubed. So then what do I raise 3 by to get 3 cubed? The answer is 3. Looking at the next example, I have two logs, each with base 5, that are subtracted together, so I could condense into one log base 5 of their ratio, left to right, 100 in the numerator, 4 in the denominator, which simplifies to the common log of 5 of 25, and 2 is the exponent of 5 that gives the input of the log of 25. Now remember that exponents is a shortcut for repeated multiplication. So that has a property as well. The power property states that if you are raising an exponent to an exponent, then you multiply those exponents. So with logarithms, when you are raising the input of a logarithm by an exponent, because logarithms are exponents, I can move that power out front and multiply it by the logarithm. I've put parentheses here in blue to emphasize that this exponent is not of the entire logarithm itself. It is merely of the input of the logarithm. So then in this example here, if I have the common log base 3 of 3 to the 4th, where this input of the logarithm is squared, if I want, I can move that 2 out front and have it double the log base 3 of 3 to the 4th. Sometimes your variable will be in the exponent position, and this is a very useful property that then moves it down into your typical algebra location so that you could then use addition, multiplication, subtraction, etc. to solve for it. But in these examples, we're going to practice with just numbers. Simplifying each expression, we have, let's see here, 6 that could then be moved out front for safekeeping. 6 times the log base 2. Now I'm going to rewrite 32 as 2 to the 5th, or I could just keep it as 32 knowing that 32 is equal to 2 to the 5th. So that answers the question of how this log simplifies, because the power is of 2 that gives me 32 is 5. And then I'll multiply it by that 6 that was out front to get an answer of 30. In the next example, I'll take the 20, put it out front, multiply it by the log base 8 of 4. Now, 8 to what power is 4 is a harder question, so we could think about it in one of two ways. The first method is conceptual. It really goes to the heart of what radicals are about, or rational exponents. 8 is 2 cubed. 2 times 2 times 2. So if I want the third root of 8, which is the same as raising 8 to the 1/3 power, that's just 2 because that's 1/3 of the numbers that are identical in this factoring of 8. So then if I want the 2/3 power of 8, then that means I want 2/3 of these numbers. So 2 2s, or 4. And then over here, and that's what we have, by the way. This is going to be, what do I raise 8 by to get 4? Well, the answer is the exponent of 2/3, because 8 raised to 2/3 power is 4. And the log is always the exponent. Or you could bring in algebra, set this part of the problem equal to x, change from logarithmic to exponential form, and then rewrite the bases so that they match. 8, 2 cubed, 4, 2 squared. And then when you raise an exponent to an exponent, you multiply them. And now with like bases, a property of equality says that we can now set exponents equal to one another and forget about the rest of the problem. And solving 3x equaling 2 gives us 2/3 x, the exponent that we had from over here. Finishing the problem, we substituted in the 2/3 that we found in one of these two methods, and then performing the multiplication and getting the improper fraction 40 on 3. Whenever you hear properties, that means shortcuts, and these are no exception. The inverse properties of logarithms and exponents. So take a careful look at this exponential equation. It's exponential because we have a base raised to a power is equal to some result. Be very careful not to assume that this is a logarithmic equation just because somewhere it has a logarithm. That logarithm is in the exponent. To show why this pattern works, that if the base of the exponent, of the base of the power, equals the base of the logarithm in the exponent, you just get what you're taking the logarithm of in the exponent as the answer. The reason why that works, circle, circle, square, is because if I were to change this to logarithmic form, so the base gets subscripted, so the log base b, go the other side to get the input of x, is then equal the exponent. You could see by a new property of equality that if you have one log on each side of the equation with the same base, then that means their inputs must be equal. And x certainly equals x. So to look at an example right away while this is fresh, let's skip down to this third one. And we see that, well, the base of this power is 5. The base of the log in the exponent is 5, and so then 10 is the answer. If you work it out using algebra, you get the following. If you set it equal to x, it's currently in exponential form, so switch it to logarithmic. 5 is the base, so that'll be the subscript. This is the long way. It doesn't use the property, but it shows what's going on. So here to there, over to here, and notice by the logarithmic property of equality, we have one log on each side, both with like bases, so therefore the inputs must also be the same. So even if you forget this property, you could use algebra, converting from this exponential form to logarithmic, and then using the property of equality to show that the answer is 10. Now the other inverse property is with logarithmic form. If the base of the logarithm matches the base of what you're taking the log of, then the exponent is the answer. Shown here that if I convert from logarithmic to exponential form, this is the base, you go to the other side to get the exponent because logarithms always equal the exponent, and then you finish this counterclockwise circle and the input is on the other side because you have like bases, then exponents must also be equal, so x equals x. So here in the first example, the base of the log matches the base of what you're taking the log of, so the answer is 11. Now here, because the logarithm is always the exponent, that gets you from the base to the input, so 3 to 81, you could just say 4. Or you could rewrite, because this logarithms and exponential equations are all about the exponents, so then you want to get in the habit of rewriting larger numbers as in their prime factorized form. So 81 can be rewritten as 3 to the 4th, and now you see this property. The bases match, so the exponent is the answer, which is 4. The last important thing to cover is the change of base formula. There are many reasons to know this. The primary one is because calculators are typically programmed in the common log or base 10, but not all logarithms, like you see in this example, are written that way. So you wouldn't be able to use your calculator in instances where, say, like the 32 and the 8 aren't related by the common base of 2. So instead, we have this change of base formula that you'll want to commit to memory, and it goes as simple as this. You take the common log of the numerator, you take the common log of the input in the numerator, and then you take the common log of the base in the denominator. And here I'm assuming that A is 10, because that's typically what people would do, and they would just use their calculator and move on. But what's really nice about this is the x is physically higher in its written position than the subscripted base is. So the one that's physically higher, not necessarily numerically larger, goes into the numerator, and the one that's physically lower goes in the denominator. And often it's going to be the common log, and I'll show that in the first example. So, or I've already rewritten it here. If you take a look for a second, I have log base b of x. I could rewrite that as, okay, this one's physically higher, so then I take the common log of that in the numerator, and then I divide that by the common log of the base in the denominator. So in the first example, evaluate, so that means to rewrite the log in simplified form to find its numerical equivalent. So if I have a calculator, I'm just going to change this to base 10. So I have the common log of 8 divided by the common log of 32. Make sure in the calculator to close that right parenthesis for the log in the numerator before hitting divide. You don't have to close the right parenthesis of the log that you're dividing by because there's nothing left on that command. And then you could simplify that, and out of the calculator you'll get 0.6. Now, there is another way to do this. The reason why in the change of base formula it's generically written as A here is because maybe I didn't have a calculator for this. So what I could do is the following. Now, why is that clever? Because I realized that 2 is a common base of both the input of the log and the base of the log of 8 and 32. So then if I change the base from 32 to 2, then I could simplify them individually because logarithms are the exponent that get you from the base to the input. And 3/5 or 0.6 is the answer. And in orange below, if you want to know where this formula comes from, I've derived it here. We don't have the algebra yet to do this step where you just take the log of both sides, but hey, what you do to one side you could do to the other no matter what it is. You could add 5 to both sides whenever you want. You could divide both sides by -3 if you want, or in this case, you could just take the common log of both sides if you wanted to. And then use the power property of logarithms, and then divide both sides by this factor, and that is a derivation of the change of base formula. One final remark going back to the power property of logarithms, and this is true for all properties, you could do them in reverse. So later, when we get to solving logarithmic equations, we will want to look at this property from right to left instead of the way it's written now. So we'll have to, as the first step, take any coefficients of the logarithm and move it into the exponent position of the input of the logarithm, and we'll revisit that later.